Hello all, good evening everyone. Welcome to my YouTube channel All About VLSI. Hope you're all doing good, right? And I hope my voice is audible and my screen is visible. Yeah. So let us start today's session. So in this session, we are going to continue with the previous topic, the diode approximation models, which we have started in our yesterday's previous session, right? So we will continue the topic. The topic name is diode approximation models. Okay, yeah. So let us start this session. So we will continue with the topic called diode approximation models. In our previous session, we have only seen the ideal diode model. Okay. So in this session, we are going to see the practical diode model. Okay. And in previous session only, we have discussed why we are going to use this diode models. What is the use of this diode models actually, and why we are going to model and why we are going to use these models. Everything we have discussed. Okay. So if you haven't watched the previous video, I suggest please go back and please watch those recordings. Okay. Yeah, it will be more helpful. Okay. Now we'll start with the topic called practical diode model. Okay. We'll start with the model called practical diode model. What is this practical diode model? So basically, in the practical diode model, we are going to include the barrier potential also. So in our previous ideal diode model, we have considered our diode as just a simple switch. Okay. So in this particular diode model, we are going to consider the barrier potential also. Okay. That is V barrier or V bias. We are going to V barrier. We are going to consider in this practical diode model. Okay, so when the diode is in forward bias, it is equivalent to a closed switch in series with a small equivalent voltage called Vf. Okay, so we are going to consider the forward voltage. So let me draw this first. So let us draw our circuit. This is our external resistor R and a diode. Okay, and which is connected to our power supply in forward bias condition. So this is a forward bias condition and this is V bias voltage. Okay, what I'm doing, I'm performing forward bias. Okay, I'm performing forward bias. Okay, now this what is a barrier potential? V barrier, which is equal to 0.7 volts. Okay, V barrier here it is equal to 0.7 volts. Okay, that is nothing but forward voltage Vf. Okay, which is nothing but forward voltage Vf, which is equal to 0.7 volts. So in forward bias condition, in the diode model, what we are going to replace this diode with is with a forward voltage which is Vf, that is barrier potential. Okay, and with a closed switch. Okay, so in what we are going to do in practical diode model, we are replacing our diode with a closed switch as well as in series with a forward potential or Vf, or it is a barrier potential. Okay, so we are replacing our diode with our voltage connected with the switch, voltage source connected with the switch, and there is external resistance connected as usual, R, and a power supply. So this is a practical model of our forward bias diode. So this is the practical model of our forward bias diode. Okay, now here the voltage is flowing from positive, here the current is flowing from positive to negative. This current is known as forward current, IF. Okay, so this is flowing through the diode IF. So the current IF is flowing through the diode and Vf is the forward voltage, which is equal to 0.7 volts. Okay, so this is in the case of forward bias condition. Okay, and the graph or the VA characteristics for this particular forward bias condition will be shown like this. So this is on the x-axis, it is equal to it is forward voltage 0, and on the y-axis it is forward current IF. Now at somewhere 0.7 volts, we will get the current. Okay, it will pass So when Vf will be equal to 0.7 volts, the current will pass through this diode. So entire current will pass through this diode. There is no resistance at all. That's why if you can see the graph is straight. Okay, there is no resistance for the current flowing through the diode. Here there is no resistance at all. In this particular portion, there is no resistance offered to this current. So that's why the VA characteristics curve, we can see there is a straight line. Okay, so this is the VA characteristics of this forward bias diode in the practical model. Now let's discuss about reverse practical model for reverse bias. Okay, this is for forward bias. And in reverse bias, what happens? In the reverse bias, the circuit remains the same as the ideal diode. Okay, so first of all, how we can apply the reverse bias? We will apply the reverse bias by interchanging our diode position. Okay, so the anode will be connected to the negative side and the cathode will be connected to the positive side. We will connect like this in this particular manner. So it will become a reverse bias condition. So in reverse bias condition, the practical model of diode remains the same as ideal diode model. Okay, practical diode model will look like this, same as ideal diode model. So it will look like a open switch. So it will look like a open switch with an external resistance here R and a bias voltage V bias, positive negative V bias. Okay, so this is the practical diode model for reverse bias condition. I hope it is clear. Okay, so this indicates that there is no current flowing through the diode in the reverse bias condition. Okay, there is no current flowing through the diode in the reverse bias condition. So the graph, the VA characteristics graph for forward and reverse bias will look like this. So I will draw for both forward bias and reverse bias. This is for forward bias. At 0.7 volts we will get the current IF, and this is forward voltage VF, and here we have reverse voltage VR. Okay, so here how much we apply the voltage, there will be no current at all. Reverse voltage, how much we apply, we will not get any current through this diode. So it is equal to 0 because it is an open switch, right? Because it is an open switch, so no current will flow through this diode. So that's why it will be equal to 0. Okay, so that is how we are going to draw a VI characteristics curve for this reverse bias. Okay, reverse bias condition. Now let us find out the forward voltage. Now let us find out the current flowing through this diode and voltage across this diode. Okay, so when the diode is in reverse bias, it is equivalent to open switch that we have already seen. And so let us find out the current flowing through this diode. And what is the voltage across the diode? VF, which is equal to 0.7 volts. Okay, that we have already seen, which is equal to barrier potential. That is equal to barrier potential. Now let us find out the current flowing through the diode. Current flowing through the diode. The current flowing through the diode can be found out by Kirchhoff voltage law. Okay, so let us apply the Kirchhoff voltage law in this particular circuit. So it will be given as, this is V bias, right? So this is V bias minus the voltage across this resistance, let's say it is VR. Okay, the voltage across this resistance, let's say it has VR. So V bias minus VR minus VF is equal to 0. So if we apply Kirchhoff voltage law, what we'll get? V bias minus VR minus VF, which will be equal to 0. Okay, so what is the voltage across this resistance R? It is given by Ohm's law. V is equal to IR. So VR will be equal to current flowing through this resistance is IF into R. Okay, so if we substitute here, what we'll get? V bias minus IF into R minus VF, which will be equal to 0. So IF into R, which will be equal to V bias minus V forward voltage. So finally, the forward current flowing through the diode will be equal to V bias minus Vf divided by R. R is the external resistance. So this is how we are going to find out the current flowing through the diode in forward bias condition. Okay, this is the current flowing through the diode in the forward bias condition. Okay, IF is equal to V bias minus Vf divided by R. Okay, and what is the reverse bias? What is the current flowing in the diode when it is reverse biased? So IR will be equal to simply 0 amperes. Okay, IR will be equal to simply 0 amperes. In the reverse bias, if you can see, it is equal to no current will flow through this circuit because it is open circuit. But what is the potential across this? What is the voltage across this? It is equal to 0.7 volts. Okay, it is equal to 0.7 volts. There is no resistance because here current, okay, current will be equal to 0, so there will be no resistance, so it will be in parallel, so V bias will be equal to this. So Vf, the voltage across the diode, will be equal to V bias itself. Okay, here we will write it. So the reverse voltage across the diode will be equal to bias voltage V bias. Okay, yeah. So this is how we are going to find out the current and voltage across the diode in forward bias and reverse bias by approximating the diode models. So this is a practical diode model. Now let us see the complete diode model. So we have one more last final model which is called as complete diode model. Let us see this complete diode model. So in this complete diode model, which is a most accurate approximation and includes barrier potential and small forward dynamic resistance. Okay, so this includes barrier potential. I hope till now you have got this term, what is meant by barrier potential, everything, right? And we have small forward dynamic resistance. This also we have discussed in our previous session, so if you haven't watched them, please go back and once revisit them. Okay, so we have discussed what is meant by dynamic resistance also. So in the complete diode model, we are going to approximate, we are going to take the dynamic resistance in consideration. Okay, we are going to consider that this dynamic resistance. Okay, now so when the diode is in forward bias, it acts as a closed switch in series with equivalent barrier potential and a small forward dynamic resistance. Okay, so let us see how we are going to model this particular complete diode model for a forward bias condition. Okay, for forward bias condition, let me draw the diode once again. So this is our diode and external resistance with a positive power supply, positive biased. Okay, this is V bias and this is external resistance R external, and this is our diode. Okay, and the current flowing through this diode will be equal to IF only. So how to model this in a complete diode model? So in the forward, since it is in forward bias, in the complete diode model, it will be equal to a voltage source, that is barrier potential, and a small dynamic resistance RD. Okay, and a closed switch. So this is a complete model of our forward bias diode. Forward bias diode. This is V bias. This is barrier potential and R. So this is how we are going to approximate our forward bias diode in complete diode model. Okay. Now, if we want the current flowing through this diode, or let us say we want to find the voltage, V forward voltage, Vf. So how to find it? So Vf, forward voltage Vf, will be equal to, if we apply the Kirchhoff law, what we'll get? So if we will apply V bias minus voltage across R is, let's say, VR minus, and Vf minus voltage across this RD, let's say it is VRD. Okay, now this V bias minus so VR is equal to I into R. So I will apply the Ohm's law here. IF I into R external, this is external resistance, right? And the forward voltage VF and minus RD. So the current flowing through this dynamic resistance RD, which will be equal to IF into RD minus IF into RD. The both currents are same. IF forward current is flowing through this resistance and this resistance also. Okay, so if you solve this equation, you will get V bias minus VF, which is equal to IF into RD plus R external. Okay, so finally what we'll get, IF is equal to V bias minus VF divided by RD plus R external. So here VF is equal to 0.7 volts since it is a barrier potential. So forward current flowing through the diode, which will be equal to V bias minus 0.7 divided by RD plus R external. Just simplifying the equations, that's it. Okay, so this is how we are going to find the current flowing through the diode in the forward bias condition of a complete diode model. So this is a complete diode model. So here what we are considering, the diode as a voltage barrier potential and a small dynamic resistance with a closed switch. Okay, so this is how we are going to model a diode in a complete diode model in a forward bias. Now complete diode model for a reverse bias condition. Okay, how to find the complete diode model of a diode in the reverse bias condition. So in the reverse bias condition, let's see the model directly. This is the R external and a open switch and a bias voltage. Okay, so this is V bias and a dynamic resistance will be present in parallel to this open switch, RD, dynamic resistance RD. So this is the reverse bias complete diode model for a reverse bias diode, complete diode model for a reverse bias diode. So this is how the complete diode model look for a reverse bias diode. So a current will flow through this circuit. It will flow through this dynamic resistance and it will reach the power supply. So this is reverse current IR. This is the reverse current IR. If you observe, this reverse current is not present in previous models, that is ideal model and practical model. The reverse current was 0 if you observe. Okay, but in the complete diode model, if you observe, we are having a reverse current also. We are having a small reverse current IR which is flowing through this small resistance, small dynamic resistance RD. So if you draw VI characteristics for this two models, it will look like this: VF, IF. So in the forward bias, after reaching 0.7 volts, there will be some resistance offered to this current. Since a small dynamic resistance is present here, so there will be a small resistance offered to this forward current IF. There will be a small resistance offered to this current IF. So in the previous cases, there is no resistance offered to this current IF in the forward bias. There is no resistance offered to this IF flowing through this diode. So that's why the line was straight in the graph. But here there is a small resistance offered to this current flowing through this RD. So that's why the line will be not straight. It will be like a small slope. It will have a small slope because there is a small resistance offered to this forward current flowing through this diode. So that's why the line is not straight. It is somewhat sloped. Now in the reverse current, coming to the reverse side, in the reverse bias, there will be small current flowing through the diode. There will be small current flowing through the diode. So it is indicated like this. Okay, due to it will flow through the dynamic resistance RD. So this is how the VI characteristics for this particular model is being drawn. Okay, yeah. So that's all for this session. So we have completed with the diode models, all the three diode models which are present, which is ideal diode model, practical diode model, and a complete diode model. So in the ideal diode model, we have just replaced our diode with a switch. If it is in forward bias, it is a simple closed switch, and if it is a reverse bias, it is an open switch, right? And in a practical diode model, we are replacing the diode with a barrier potential. We are considering the potential of the diode. Okay, so we are replacing it with a voltage source. Okay, we are replacing it with a voltage source. And in reverse bias, it is replaced by a open circuit. It is replaced by open circuit. Okay, and in a complete diode model, we are replacing the diode with a barrier potential as well as a dynamic resistance. Okay, whereas in the reverse bias condition, we are only considering the dynamic resistance. Okay, so that is about the three type of models which are present in the diode approximations. Yeah, so I hope all the concepts are clear and you have got a clear idea about all these three types of models. Okay, so yeah, so that's all for this session. So if you're having any doubts or queries, you can ping me in the chat, or else we can end this session. Okay, thank you. And if you like this video, please like, share, and subscribe to my YouTube channel, All About VLSI. Thank you.